Acids and bases are things that get inside water, dissolve, and either form H+, which is hydrogen. When it reacts, it loses an electron to become H+, or OH-, which is one of those groups that we had to learn as being a ionic group. Particularly acids, when dissolved in water, they taste sour. Now here's one thing I don't want you to do. I don't want you to go into any chemistry lab and try to figure out if it's an acid or base by licking it, okay? Now, why in the world do we talk about things tasting sour? Does anybody like sour candy? Yeah. Have you ever seen those places where you can go in and you can just get the powder directly? And some of those acids are, some of those sour things are very, very, really sour. What they are, and there's an entire industry that creates organic-based acids that are eaten. One acid that you might use in your cooking, and sometimes when you have fish and chips, you put vinegar on it. Vinegar is one of the simplest organic acids. It's sour. But it is an acid, but it is considered a weak acid. So if you think about an acid, you put your hand in an acid solution, you think about your hand dissolving, right? Well, there's all sorts of strengths about how acidic something is, and so some acids we can eat, but if you do put your hand in some containers of acid, it can eat it away. One of the indicators that we use, and the animation showed this, there is a dye, a color, that if you put it in acid, it'll change to red from blue. And if you put that same dye into base, it'll turn it from red to blue. It is a organic molecule that has color, like you dye your shirt with something. And they react, or several of the dyes that are used can react with acids and base and change from one color to another. And we're going to use a piece of paper that is soaked with these colors, these dyes, which are going to help us identify if something is an acid or if something is a base. The most basic one is you have red paper, see if it turns blue. You have blue paper, see if it turns red. But we now have a combined strip that will be able to give you a color all the way from 0 to 14 on one piece of paper. It's a little bit more expensive, but it gives you a lot more data. Acids tend to react with metals, and when they do, they form hydrogen gas. Hydrogen is a diatomic gas, and it's explosive, and so quite often when you hit metals with acid too concentrated, if they react very fast, they can produce a lot of hydrogen, and it is not great. Acids can burn your skin and clothes, but acids can be inside your stomach and digest food. Now, our stomach is designed to have acid, and the type and concentration of acid is about on the order of battery acid. It's almost about the same, but our bodies are designed to contain that acid when we eat and then neutralize that as it goes through our digestive system. Now, sometimes we have overproduction of acid in our stomach, and you get a burning in your esophagus, a heartburn. That's not nice, is it? What we do is we tend to give people antacids, meaning we give something to react it with and to neutralize or take away the acid. The problem is you can neutralize it, but if the acid has already interacted with your esophagus, it could burn it a little bit, and then it needs time to heal. And so it sometimes isn't immediate relief, but it can be it can stop the damage. One thing about digesting foods with acids. Does anybody have? Nope, no one has a can of Coke. If you actually, oh, you do. The ingredient list. Is there an ingredient list on that Coke can?
Yes.
Okay. So the first thing is water, and the next thing is probably high fructose corn syrup. Yep. And then the next thing is?
Caramel color.
Okay, so it makes it brown. What else?
Phosphoric acid.
phosphoric acid. There is acid in most soda cans. And that phosphoric acid is not killing you when you put it in your mouth, and it doesn't kill your esophagus, and it gets into the stomach and it gets mixed with something that's very acidic, and then it gets neutralized out. But it is acidic enough to do this. There's an experiment that a lot of elementary school teachers do to show how acidic that Coke is, and it mimics what happens in the stomach. Acids can break down protein. So if you take a chunk of meat and you take a glass, you put the chunk of meat in the glass and you pour a Coke in it, and you fill it up, and you set it there. So they have seen the chunk of meat go in, and you filled up the glass, and you let it sit for about a week. If you pour out the Coke, there's no more chunk of meat. It would have been dissolved or broken down by the acid content inside that Coke can. And so it is enough to be reactive, okay? It is acidic, and what's really odd about it is that if I take that Coke can, and since I'm in a laboratory setting here in the science department, if I go in and I go to the sink and I pour a Coke can down the sink, I can actually be fined because I am pouring acids down the sink. I'm under much different regulations than you are at home. Okay, and so the pH value, the acidity level of that, I am not allowed to pour that down the sink. I would actually have to bottle that up and send it off and be paid to be destroyed if inside the laboratories. That's what I would be required to do. It's kind of crazy, but what they're trying to do is from laboratories not put things down the drain that might affect our city water and the treatment. And so you don't want us to be putting chemicals down our drains, even though it might seem weird for some of the rules for us. The chemical story for an acid is this. When a compound like hydrochloric acid, which is really a gas, if you actually have it pure, it's in gas form. If you dissolve that in water, the acid reacts with the water, and we said it gives a proton. Okay? And for chemists, since we're lazy, we write this all the time, H plus floating around. But what really happens is that water looks like this, and an acid reacts with water to make H3 plus, what's called the hydronium ion. That is what's really floating around inside. The acid reacts directly with the water, and it reacts in such a way that the reactive species effectively is this. So chemists are lazy. We'll write H plus a lot of times, but really it's floating around as H3O plus in the water. Okay, and so it's just convenient. You may see both of those written some places. Oh, the other part of the story. This arrow that goes in one direction means that all of the hydrochloric acid gets broken apart into H plus and a Cl minus floating around. All right. There's another chemical story that I'll show you just a bit. That's a different chemical story. Bases, on the other hand, when you put them into solution, they will interact with the water, and by the end, it will create more OHs floating around than when it began. It tastes bitter. Okay. Now, if you had a mama that didn't like some language, sometimes you get your mouth washed out with soap, and you can taste it that way. Hopefully, no one has ever had that experience. But the hydroxide, the actual base, when you wash your hands with soap, it feels slick, right? It is not because of the soap. It is actually because of the residue of hydroxide. If you actually get base on your hands, it feels like you have soap on your hands. It's slick like that. It's because of that chemical, not the soap itself. Soap is made with hydroxide with base. And so a little bit of residual is left in most soaps, unless you have Dove, which is pH balanced for your protection. Okay. Again, it turns the dye litmus from the red state into the blue state. It is also destructive to flesh and clothing. Okay, so it will eat things up. In actuality, if you splashed acid on your hand and you splashed the same amount of, or same concentration of base on your hand, all right, the base will actually burn worse than the acid. The reason is, just in your chemistry, your hands are just a tad acidic. That's just the normal biochemistry that happens in your hand. And so acid doesn't react with acid, but base reacts with acid, and so a base burn can actually be worse than an acid burn. I'll tell you this, I know that both acids and bases are very destructive to clothing. I used to teach freshman chemistry labs all the time. And so when people are working in the chemistry lab, for the first semester, they don't know what they're doing. They have no idea. And so they may be a little bit sloppy and things may drop and spill and splash a little bit. Now, I would wear a lab coat and that would catch most of the thing, but the lab coats only come up to like right here. The bottom of my pants would get acids and bases on them, but you don't see it right away. You only see it after you wash the pants and it mixes up with the water, and so by the end of the semester, my lab pants would be full of holes down near my feet because of all the spills that would happen. So I'd have to throw them out and buy a new pair. And so I would have lab pants so that those were the ones that got eaten up by the acids and bases. Now, acids can be weak and acids can be strong. Now, you probably will think about this in a different way in terms of weak and strong, and I'll compare what you might think about. Weak and strong, you may think about, you may have default to this. Is it, if I put my finger in it, is it going to totally burn up really quickly, or is it going to take a long time? That's not necessarily what we talk about in terms of weak and strong. Strong means that if you put it in water, all of that compound will be broken up into the proton or the hydroxide. Okay? And so you can have a little tiny bit of strong acid or strong base that will completely make the acidic solution or the basic solution. The chemical story is told this way. I have a arrow that goes only in one direction. And so I start with this, but I end only with this in the solution completely. A weak acid happens this way. I place it into the water. Some of it breaks apart into, in this case, this is the acid. But as it's floating around in the solution, some of the acid reacts with this and goes back the other direction. And so in the solution, I have a little bit of this, a little bit of that, a little bit of that, all floating around. So not all of it is in the acidic form or conversely the basic form. Some of it is the original, some of it is the acid base, and some of it is the anion. The chemical story says that the reaction goes both ways. And we also call this an equilibrium. There is a distribution between them. In terms of strong and weak, how they behave when they get in water. Another way that we think about, and the way that you might think, is it going to burn me immediately in terms of strong and weak, is really how concentrated is the acid. Do I have a lot of the acid in there, or do I have a little tiny bit? And that's more relational to, is it going to really hurt me if I get one drop on or not? Most of the time, when we have experiments in lab, we use strong and weak acids, but at very low concentrations, so it doesn't hurt people. Okay? But my TAs who do lab prep have to go to the concentrated bottles and make up all those nice diluted solutions for you to use. And so they have to be trained very well. We make sure that they know their lab technique so that when working with very concentrated strong acids, they're not going to drink it. Just got to make sure that they won't do something like that. Now, how we measure how acidic the solution is, we're actually measuring a very, very tiny amount of either protons or hydroxides. It is so little, it can be as little as 0.00000001 or 13 zeros and a 1. That's how small the concentrations can be, and that's a weird number. So what we do is we take a scale that goes from 0 and goes all the way up to 14. And that is the range by which things can be acidic. Things that are absolutely not acidic is pure water. That's by definition, and we have a value of 7. So if something is around 7, it is neutral, not reactive at all. If the numbers go to smaller numbers, that means it's becoming acidic, and the higher or the lower the number, the more acidic things are. And so battery acid up there and stomach juice are very acidic, and you don't want to spill any of that on you. Conversely, as I get the numbers larger, they become more basic. And so our bodies are made up of a lot of water, but some of the stuff that's dissolved actually makes our blood just slightly basic. And so it's about 7.4 is where your blood is, where 7.0 is perfectly neutral. Seawater is a little bit more basic. You get to soap with residual hydroxide as part of the synthesis. That's it. Ammonia is a base. And then if you take a look at hair remover like Nair and oven cleaner, they're closer related to each other. And so if you've ever used hair remover, you know you can't leave it on too long, right? You will be burned. Why? Because it is very, very basic. All right. If we go the other route, your saliva is a little bit acidic because that's where digestion starts, and most of our digestion needs acid. And so we have a little bit of acid in our saliva, and it gets more acidic as we go to the stomach. If you drink coffee and tea, your urine is also acidic. All right. Grapes and tomatoes are very acidic, but they're in very low concentration, so it gives you a taste, but it doesn't burn you. Vinegar, if you drink it, it's very acidic. The Coke, really acidic, and not here at Lee. And we have lemon juice, again, very acidic. But again, lemon juice, depending upon, can be really less concentrated, and sometimes you can get some lemons that have a lot of acid in them. And it can actually, some people could be sensitive to trying to eat them or using the juice itself. It's so funny when you give a baby lemon at a restaurant. It's just, but that, I digress. All right. Now, pure water is neither an acid or a base, but it can dissociate. Okay, it can dissociate into an H plus and an OH minus at the same time. But the reaction goes back, an H plus an OH makes H2O water. Now, what the distribution is, it occurs, it's like this. For every 2 of these, you get 1 billion of those. So in the equilibrium, it lies way over on one side. And so there's almost no protons and hydroxides running around in water. That's what we call neutral, or that is our reference scale. And so if I just make it any more than 2 in terms of protons, then I will be acidic. And if I make it any more than 2 hydroxides in that billion, I make it basic. Now, acids and bases do a very special reaction. It's called neutralization. I take an acid and I take a base, and I create water and what's left over. What's left over is this cation and this anion. This right here is a salt. And so you see sodium chloride and you know that as a salt, but for a chemist, any salt is this. When any acid and any base react, whatever the other two things are salts. They're an ionic compound. Okay? And so for us, a chemist, salt is a much broader term than what you think about. And so if you are, let's say, have high blood pressure, and your doctor says no salt, what you can substitute is sea salt. Okay, well, what in the world is sea salt? Sea salt is all the other salts that are in the ocean after they've taken out the sodium. What people are concerned about is the sodium content, and that's what really is what the high blood pressure comes back. But the salt and sea salt is all the other things. And it can bring flavor, it brings a little bit different flavor, but it can bring flavor without the same effect as sodium chloride. And so salts are different. Now, here's one thing. The pH of water is neutral. If you dissolve a salt inside water and it floats around, it's still neutral. So I can dissolve things in water and it still be neutral, not an acid nor a base, because whatever I dissolved in it didn't turn into an H plus or an OH minus. And so I can have lots of things dissolved in water and still be neutral pH. But there are some things I put in water and all of a sudden it becomes very, very acidic or very, very basic.